So in this video, I'm going to introduce all the things we're going to talk about in this lecture, starting with our learning objectives, and then dive into the first half of our goal today, which is understanding some more tools for asymptotic analysis. So again, with I state learning objectives, they might not make sense right now because I haven't introduced these concepts yet, but it's important to, when you look back, to see these. So I want you to be able to differentiate between big O, big omega, big theta, come up with big O, big omega, big theta bounds for a given function, perform case analysis to identify best case and worst case, and describe the difference between case analysis and asymptotic analysis. So this video is going to really focus on those big three, big omega, big O, and big theta. And the next video is going to talk about this thing called case analysis. So to kind of recap where we were from last lecture, we introduced this whole process of algorithmic analysis, where you start at code, and your first step is code modeling to turn it into a function describing its runtime. And remember, it could really describe anything, but by default, we usually assume runtime. And then once you have that function, you could then apply asymptotic analysis to then find a complexity class or a big O bound. And this was our whole pipeline where we went from code modeling to a function and code to a function and code modeling, and then a function to complexity class in asymptotic analysis. And today we're going to actually show you how to expand both the asymptotic analysis and code modeling portions to give you some options. So this video, again, only is going to focus on asymptotic analysis. Before we go through this, I want you to actually try and do a little bit of practice. So as a bit of recap, which of the following functions are big O of n squared? Select all of that apply, and I'll give you a minute to try this out. Okay, so hopefully you're able to have an idea of what we mean by big O of n squared, which ones of these apply. Remember, big O here is an upper bound. So I'm asking for any function that's upper bounded by n squared. So f1 is not going to be big O of n squared because it grows in cube-like fashion. So squared will not upper bound this term. It might be bigger at some point when n is small, but as n gets larger and larger, this n cubed term is going to blow up and get bigger than n squared. So remember, big O means upper bound. What about f2? Well, that's a really big constant. But remember, constants aren't going to change growth. So even though that constant term is huge, eventually n squared, because n squared will always get bigger as you increase n, can eventually dominate that. So this function, f2, is big O of n squared. Similarly, because the dominating term of f3 is 2n squared, that's an n squared term, so it's going to grow at most n squared like. And so we could upper bound that with n squared too. And remember, even though there's that constant in front and those extra terms, you could drop all those away because in the end, when n gets really, really large, that n squared term is going to be the one thing adding on to it. And then as a bit of a reminder from the practice problems we saw on Wednesday, when you have logs grow slower than n. And so since log n is less than n and n is less than n squared, you could pretty easily argue that this log n term will be big O of n squared. So again, big O is an upper bound. And as a reminder of how we do this process, when we're doing asymptotic analysis, we're going to be given a function that models some piece of code, and we want to characterize that function's growth rate asymptotically as n approaches infinity. Now, one thing to highlight here that's a little bit different, we've been a little nebulous about what we mean by n. In all of the examples we've seen so far, n has been like the input of a number, like the number that's being input. And we talk about how our algorithm would scale with that input. Most of the time in this course, after this week, when we talk about n, we're going to be talking about the size of a data structure. Because usually we're going to be worried about how do these algorithms scale when I'm using a particular data structure. And so we usually use n to describe the size of that. But remember, the code modeling step is supposed to come up with a function that describes the runtime in terms of the input size. And so the input size kind of depends on your context, what your input is. And so if it's just a simple number, we're talking about n being the number itself. That's why one of our unsaid assumptions here is that n is only going to be non-negative integers. We don't worry about negative input sizes because those don't really exist. And also, for most data structures, the input size will be an integer value. You can't have half an element in your data structure. So that's generally an assumption we've been making. Now remember, big O is an upper bound. We ignore the constants in small terms, and the big O does not have to be tight. So this function 10n squared plus 8 is both big O of n squared, big O of n cubed, big O of n to the fourth, and big O of n to the fifth. It's a big O of all of those things, and even more. Anything that upper bounds that function is good. We generally will ask for tight bounds, so ask for the smallest big O bound, but it's good to remember that big O just means upper bound. It does not mean anything about exactness. And we also showed you a proof of big O. I'm going to hide my video so you can see that proof a little bit better. When we had, or sorry, not the proof of big O, but the definition of big O to really remind us what it's asking. And so our formal definition was f of n is big O of g of n if there exists some positive constants c and n naught, such that for all n greater than n naught, f of n is less than or equal to c times g of n. What that's really saying is some long-winded way of saying that g eventually dominates f. It will eventually grow faster and always upper bound it from n naught onward. So intuitively, the reason this definition has those constants that you need to choose is that we don't care about small values. We care about large values as n grows asymptotically. And so whenever you want to do a proof, and remember, we're not going to ask you to do these proofs, but it's good to understand what the proof entails. You always just need to choose this constant c and this constant n naught to show that f is less than or equal to c times g of n for all n greater than n naught. Always a mouthful. So for example, I've shown you 3 mini proofs here. Suppose the function you're looking at is 0.5n, and you want to show that's big O of g of n. Now, when you look at this picture, if you look at with our intuition at this, you're like, oh, drop constants, lower order terms, it's definitely a big O of n. But the proof of this involves showing that these two constants, c and n0, exist. Since 0.5n is always less than or equal to n, for positive, we always are just going to be considering positive n. It's a pretty straightforward proof. You could just pick any constant. I chose the constants 5. There's no need that there needs to be a unique constant. Usually there's an infinite number of constants that you could choose. So I chose c and n, and if you do a bit of algebra, you could show that this function is less than or equal to this function when you plug in these constants. So that's great. That's how you do this proof. This also works for whenever you're scaling a function. So when f of n is 2n, you can also scale g appropriately to make sure that that upper bounds it, because we're still trying to get that growth, how it scales asymptotically. We don't really care about those constants. And it works when the functions crisscross at different points, as long as one eventually dominates the other. So in this last case, we could show that f of n is big O of n squared, because eventually, once n is greater than 1, so I just picked a number 6, n squared is going to be larger than n. And it just chose a constant for fun. Remember, these constants don't have to be unique. You don't have to necessarily be clever about choosing them. You just have to show that this less than or equal to the relationship holds for all n greater than n naught. We showed you that on Wednesday, we showed you that how you could do a proof using this that for when there's like multiple terms. And remember, the proof is not the learning objective. If you want to talk about it, it's kind of interesting, but we're not going to focus on that today. We're just going to focus on this intuition of the definition. Okay. So now, why am I spending so much time reviewing this? One, because it's a bit confusing the first time you see it, and we want to make sure everyone has a solid foundation. And the reason that solid foundation is important is because it allows us to be rigorous when analyzing more complex pieces of code. So I'm going to take us to some uncharted waters. So I have a function here called isPrime, and its job is to return true or false, depending on if the input n is prime. Remember, prime numbers are ones that are only divisible by 1 and itself. So like 3 is a prime number, but 4 is not, because 4 is divisible by 2. And so you could write a pretty simple method to do this. You start at 2, you loop through until you reach n, and you just check if every single number is divisible, can divide your input n. If you ever find one that does divide it, you can return false because it's not prime. Otherwise, return true. And so now our goal is to find, okay, well, let's do some algorithmic analysis on this. The first step is code modeling. How can I model this runtime in terms of the input size? And so we know how to count operations. I just did all those at once. Remember, the exact +1 or +2 does not matter. We are going to throw away all constants. I could have just put +1 for all of these. I could have put +14 if I was feeling kind of fun today, because we're just going to throw it away anyways. Those constant numbers don't matter. We just know it's just some number of constant steps. But it's not just enough to take up each line and say how many steps are in that line. You also need to account for loops. So we have this while loop here. And so that whole loop itself has approximately 5 steps. I think if you add up the numbers I have on the slide, it's actually 6. But again, I'm trying to emphasize that loosey-goosey is okay with constant numbers. And the reason I'm going to keep forcing us to be fast and loose with this is because eventually we're going to just stop the effort of counting constant steps. So it is just not worth our time to say, why is that number +5 instead of +7? Because we're going to drop it anyways. It's just irrelevant what number is actually there as long as it's a constant. So the question is, okay, it's doing some constant number of steps, but how many times is it going to run? This is a bit tricky to answer because sometimes it's going to stop early. Like if n is even, it's going to stop on the first iteration of the loop. But if n is not even, it's kind of hard to figure out how many times it'll run. Sometimes it's going to need to run all n times if n was prime. It's going to have to loop through every single number between 2 and n because none of them will actually divide it until the very end. So the number of times this loop runs is actually really hard to answer. So what I've done on this next slide is I've actually plotted the runtime here for as you increase n. And you can see this pattern of sometimes it's fast and sometimes it needs to loop n times, where you see some of these dots, the prime inputs n, take a lot of time, while the non-prime ones take relatively short amount of time. And so you might come up with, looking at this code, well, sometimes it stops early and will have maybe a constant number of steps. So maybe I'll say this is big O of 1. But sometimes it needs to run a proportional to n times, and so then maybe you'll say it's big O of n. And our intuition here is just not going to really help us, because this is a complex example. In some sense, our intuition might say that both of those are right, because more than half the time, it's going to be a really fast operation, right? Half the numbers are even numbers, and so it's going to end in just a couple steps. But there's always going to be a bigger prime number. There's actually a proof that there's an infinite number of prime numbers. And so it's also going to, every once in a while, have one of these really slow ones. So this is why we need formal definitions. We need to know what big O is actually saying in order to answer this question. So remember, the big O definition says that a function is big O of something if that function is upper bounded by that other function using our constants. So looking at this function, remember, this function isn't really nice. It's not like a smooth line. It kind of jumps up and down. But it's still a function nonetheless. It takes an input and reports an output. So is the runtime of this function big O of n? The way you answer that is, well, if we're trying to do a proof, you could say, well, can I find constant c and n naught such that this function is below O of n, or a function scaled with n? And so if I chose something like c is 1 and naught is 5, you could show with a bit of an argument that this is definitely going to be true. You could definitely see this just visually. An easier approach is a visual proof that this line, if you draw a linear line like this, is going to upper bound this function. Because in the worst case, it's going to in the worst case, you have an input that makes it run n times. So that's definitely going to be less than or equal to n. And so that's a bit hand wavy, but again, we're not trying to do proofs all the time. Can you say the same thing for O of 1? Can you find constant c and naught such that this function's upper bounded by big O of 1? And the answer is no. If you choose any constant, say c, you can always find a bigger prime number. And so because this function takes a long time to run on prime numbers, this function will not be upper bounded by a constant. And so we know from our definition, it's not big O of 1. It's big O of n, not big O of 1, because big O of 1 does not upper bound this kind of part of it that grows linearly. So that's really important to remember. The definitions help us guide our answers to this question. Now, I will mention that even though we report that this is big O of n, and in fact, big O of n is a tight bound, you can't find something a bit smaller than that because those kind of points up there take n-ish time. But it's a bit unsatisfying because this function is definitely a lot better than O of n a lot of the time. A lot of the time, it's like close to constant time. Consider another example of like printing all the elements in a list. Well, that's going to take n time if there are n elements in the list because you're going to have to loop through all of them. These two functions behave very differently, but they have the same big O. And in fact, both of those big O's are tight. They're tight bounds. So it's a bit disappointing that the big O is the same here. And that kind of goes to the fact that big O is not precise. It loses a lot of constant and low-level details. So what would be nice for us to have is also a tool for talking about what's the lower bound. Is there a way of saying that printing this list, printing the numbers in the list, takes at least n operations, whereas the prime number can sometimes be faster? So the question there is, can we talk about how much work at least do you need to do? And so enter the Greeks. So we're going to talk about this new thing called big omega. Big omega looks a little scary at first, but if you understand big O, you understand big omega. Big omega is just the flip side of big O. Where big O is an upper bound, big omega is a lower bound. And you could tell it's a lower bound because it has its little feet on the bottom in the character. So big omega is about lower bounding a function. And I'll read off its definition for completeness sake, but it's almost exactly the same as the big O definition. F of n is big omega of g of n if there exists some positive constant c and n naught, such that for all n greater than or equal to n naught, f of n is greater than or equal to c times g of n. Notice that big omega and big O definitions are exactly the same character by character, except the O and the omega, and the direction of that less than or equal to. So big omega is finding a function that lower bounds the function of interest, while big O is about upper bounding it. So f of n is big O of g of n, means f of n grows at most as fast as g, and f is big omega of g if f grows at least as fast as g. And so you can see here that you can lower bound this function by a constant. You could say it's big omega of 1, because sometimes it's going to take constant work. So it's going to be constant work or above. That's what big omega statements are saying. You're saying it's going to take at least this much work. It is a lower bound, while big O says it's going to take as much as this work. It is an upper bound. Now, just like big O, big omega does not need to be tight. So for example, consider the function 2n cubed. That is big omega of 1, big omega of n, big omega of n squared, and big omega of n cubed. Any function that lower bounds it, it could be big omega of. So these things, oh, sorry, I didn't mean to fast forward. This big O and big omega can be loose. They don't need to be tight. But if you find tight bounds for big O and big omega, it tells you a lot about the functions. So consider our printing example on the right. F of n is equal to n. We showed earlier that it's big O of n, and this thing will also be omega of n, big omega of n, because it's going to be lower bounded by this function. Notice it's also big omega of 1, but big omega of n is a much better description because it's a tight bound. Most functions we'll see in this class will look like this, where the big O and the big omega agree, and they're kind of just this nice line or nice curve. But this doesn't always have to be the case, like our prime example. And in our prime example, we can show that it's big omega of 1, but it's not big omega of n. And the reason is you can't lower bound this function by a linear one, because a lot of those things take constant time, right? So while big O is upper bound, big omega is lower bounds. So since most of the time big O and big omega agree, we have one last notation to introduce to kind of convey that fact, that it's kind of this nice case where the big O and big omega are both tight and agree. And we call this last one big theta. So again, big O, upper bound, my code will take at most this long to run. Big omega is lower bound, my code takes at least this long to run. And if those things to agree, we can talk about a big theta. Big theta is equal to. And so you can think of this saying something like, my code takes exactly this long to run, but with all our caveats from our asymptotic analysis that we ignore constant factors and lower order terms. This only will exist when big O and big omega agree. So the formal definition of big theta, and theta is this symbol, this first symbol in this last box, with this, it looks like an O with a little line through it. That's a theta. F of n is big theta of g of n if f is both big O of g and big omega of g. And so what you're saying there is that that function g serves as both an upper bound and a lower bound with different constants, right? Like you might use a bigger constant for the upper bound and a smaller constant for the lower bound, but it still is a tight bound for both. So this will exist if they agree on them. So in this example, when I showed you just this linear function printing all the numbers in a list, it's both big O of n and big omega of n. Therefore, you can say it's big theta of n. Big theta is a tight bound, saying that big O and big omega agree. And so if you report, when someone asks you to do an asymptotic analysis and you say, oh, it's big theta of n, that gives them a lot of information because that tells them both the upper bound and the lower bound. Whereas big O only tells you an upper bound, or big omega only tells you a lower bound. Now, and this is just me showing the definitions again. So now we have upgraded our asymptotic analysis tool. Instead of just having big O, we now have a choice. You can report the big O, or the big omega, or big theta. And remember, since big O and big omega are upper and lower bounds, usually people prefer the tightest possible answer, so you don't just give a lame answer like, oh, this really big number. But you can use our analysis to find big O, big omega, or big theta. And so now you have choices here. How do you want to report something about this runtime? Does it take at most this time? Does it take at least this time? Or does it take exactly this amount of time? Which gives you a lot of information. Now, even more important, or more usable, is these things don't always exist. Remember, big theta is only going to exist if big O and big omega agree. And so if you look at our prime example, since the big O and big omega disagree, there is no big theta for this function. So, but that information can itself be useful in characterizing this function, because we know it's going to be going up and down in some sense a lot, because we can't lower bound it by a linear function. And so having this can be very, very useful when thinking about trying to analyze a function. So now where are we in our pipeline? We've just expanded that asymptotic analysis. You now have choice on what you want to report. You could report one, you could report all three, whatever you're trying to convey. In the next video, we're going to talk a bit about code modeling and show you some other choices you can make there.